A quantum computer uses the rules of quantum mechanics to quickly solve certain problems. I know that's really abstract, so let's break it down. First of all, quantum computers will never fully replace classical computers. In fact, you need to have a lot of classical computers to operate all the quantum parts of a quantum computer. Quantum computers need two things. First of all, they need a quantum system for its qubits. Qubits are the zeros and ones of a quantum computer. They're usually made out of atoms or systems that can act like a single atom at a time, which means that qubits can reside in a superposition of 0 and 1. Let's assume that a pendulum is a quantum system. It's not. It's too big and I can measure it. I can look at it without affecting its motion. But when it's excited, it's oscillating, which is exactly what real quantum computers do. And so for my quantum pendulum, I'd want to know, is it oscillating or not? But a superposition can only tell me what's the probability that it's in one state or another. The second thing they need is for the qubits to be entangled, or for them to interact with each other in a close way. We can entangle our pendulums by putting them on the same string, so that the motion of one is affecting the motion of the other. Notice how these two pendulums are basically taking turns as who gets to oscillate the most. If I add more oscillators, I'll get more complicated behavior. But there are certain behaviors that are going to be much more likely than others. And while these behaviors aren't doing calculations, there are algorithms that can interpret the more likely behaviors as being the result of a calculation. I'll talk about one of these algorithms tomorrow. But the key here is that by studying how these large systems of particles interact with each other, lets you do calculations that a classical computer just can't. And that's why there's a number of researchers so excited about quantum computing. Thanks for watching.